Hi, I'm Natalie Pagler, Chief Health Informatics Officer at Stanford Medicine Children's Health, and it's my pleasure to introduce Peter Lee, Corporate Vice President of Research and Incubations at Microsoft. In that role, he got a significant head start on the rest of us in experimenting with ChatGPT. Before Microsoft, he was professor at Carnegie Mellon University. He served at DARPA on President Obama's Commission on Enhancing National Cybersecurity and on several boards. He's also a member of the National Academy of Medicine. And with Carrie Goldberg and Zach Kahani, he co-authored the book, The AI Revolution in Medicine, GPT and Beyond. Welcome, Peter.
Thank you, Natalie, and just thank everyone who's been organizing this great summit. I was jumping in and out of the talks yesterday, and it just really looked fantastic. I wish I could have devoted more time, and so I'm really honored to be here. Also, just listening to bits and pieces yesterday, I just realized just how far along folks are in the kind of Stanford ecosystem in AI and medicine. And so it did make me rethink a little bit about what I should talk about. So let me go ahead and share my screen and we can get started. I'm accustomed over the past year, since, as you say, Natalie, I had this head start to talking to non-technical newcomers in the healthcare industry, in medical research centers and so on. But it became clear yesterday that that's not what we have here. I mean, I think people are thinking very hard and very sophisticated and advanced thoughts here, and that's very exciting to see. I couldn't be more impressed and more pleased to see that. And so what I thought I would do is instead try to say a few words on, where is all of this generative AI stuff heading when we're talking about healthcare and medicine. And, it's something that I've had only a little inkling about. In fact, I have a bad joke about a question like this, which is when you all figure this out, please tell me. But I do have a few thoughts, and I thought I could at least frame some questions. And maybe this will stimulate more questions, Natalie, when you and I have time for some Q&A. And so what I thought I would try to run through very quickly is the following. What will generative AI be used for over the next year, next 3 years, next 8 years, next 15, 20 years? There's tremendous, of course, curiosity about the nature of the AI models that we'll be using. Will we have a world with one big brain in the sky, one big generalist model, or maybe a small number of them, or are we going to live in a world with many specialized models? What is the role of specialization? People are starting to talk about not just LLMs, large language models, but SLMs, small language models. And indeed, some of the computer science progress in small models and especially open source developments are getting to be very exciting and very interesting. So will that be a factor in all of this in the future? What about multimodality? Of course, in medicine, you have not just text, but you have images, you have many different kinds of signals, and increasingly also we think about what happens in the chemistry of our cells. And all of these things, of course, speak to different kinds of modes. Also, many of these things are only partially or not at all products of human thought and action, but are products of nature. And so what about that? How does that factor into things in the future? And that, of course, also leads into questions about not just the delivery of healthcare and the advancement of medical science, but also the life sciences and the impact on biotech. Look, I don't have answers for all of these things, but I do have some thoughts that I would share, at least to frame the thinking about these things, because I think all of these things will be important for our futures. Now, there are other topics I also thought about. If there's time, I have a somewhat silly way to explain generative AI to non-technical newcomers that's turned out to be fairly effective. And so I'll try to share that if there's time. there are, of course, very interesting questions about the nature of hallucination. I think that that's going to be less and less of a topic as time goes on, but it's still very interesting, as well as questions about bias, the ability of these large language models to manage privacy, and then how is the regulatory landscape going to evolve? And then, of course, every healthcare organization that I talk to, especially in leadership, wants just the concrete, tangible advice on how do I adopt this? What's the roadmap? And so these are all things, but I'm hoping that we can at least quickly go through these first 5 topics in a framing way. All right, so let's start about what will generative AI be used for. Back, it was now more than a year ago, it was back in August of 2022 when I was first exposed to what we now call GPT-4. And I should say in my talk here, I'll be focusing primarily on the model from OpenAI that is known as GPT-4. You can access GPT-4 by being a ChatGPT Plus subscriber from OpenAI, or by using the Bing search engine and accessing the chat feature, or if you are an enterprise, you can subscribe to the Azure OpenAI service, and those are all ways to access GPT-4. And so the first thing, of course, that I wondered about in thinking about the potential impact of a model like GPT-4 in healthcare medicine is, does it know anything? Can it diagnose things? Can it suggest treatment options and so on? That's a question that I'll get to later that I think has become distinctly less interesting over time. But in an example like this, where there's some medical vignette, and actually the first thing I tried to do was subject GPT-4 to questions from the US medical licensing exam. It was shocking to me at that time, now more than a year ago, that about 90% of the time GPT-4 would give reasonably correct answers. And what was even more kind of interesting and shocking to me at that time was it wasn't just giving answers, but in the words that it was spitting out, it seemed to be exposing signs of causal reasoning, the chaining of causes and effects, counterfactual reasoning, coming to conclusions on the basis of what is known can't be true, and even some hints in some cases of planning, all things which at that time I thought, in fact, I felt I knew to be impossible in the neural transformer architecture. Since that time, of course, we also run into problems. The system, while it gets typical kind of medical consult or USMLE problems correct 9 out of 10 times, it also makes mistakes. Those 1 out of 10 times are troubling. And sometimes the mistakes are hard to assess because the words that are spit out by a GPT-4 are expressed in very confident manner. And so it felt important to try to educate the medical community as quickly as possible to understand the nature of this thing. And over time, it has become very apparent that having a human in the loop is important. But even more than that, for things like medical diagnosis, I personally recommend, given the current state of technology, that doctors and nurses, other clinicians, do their own work. And so here in this conversation, you see that I am coming to a conclusion. It turns out to be an incorrect conclusion, but I, as the human being, are coming to a conclusion about the diagnosis, in this case of acute rheumatic fever. And that allows then the model to do an evaluation or critique of the human's work. And the thing that we've discovered, over the past year and a half or so, is that while the system can make mistakes, while it can hallucinate, it seems to have extremely strong ability in doing a critique or review of work developed by human beings or by other AI systems. And so in this conversation, you can see that GPT-4 is given the chance to assess the decision that I made about acute rheumatic fever, correct me and say that actually low serum concentration of C3 is more associated with PSGN, and we have a better diagnostic outcome. Now, while all of that, I think, was the initial sort of focus of attention, and just as a techie, I think I'm like most technologists. When we think about medicine and medical technologies, we always seem to think about diagnosis first. I'm not too sure why that is, but it's the first thing we think about. But as you get deeper into this, you start to realize that diagnosis is such a small part of medicine. There's so much more. And in fact, even in the healthcare delivery part of medicine, there's a lot that goes on. For example, one thing that happens is just a tremendous amount of administrative or clerical or documentation work. And so as time has gone on, at least for me and my research groups within Microsoft Research, as well as our collaborations around the world, and our own business product developments within Microsoft through our Nuance business, we've tended to focus less and less and put less and less of premium on medical knowledge tasks like that, and more on general cognitive tasks to perform functions like the creation of medical documentation. In this case, writing justification text, maybe for a prior authorization request, or producing medical notes in standardized formats like SOAP. And what we have found over the past year and a half is that the potential value and the high value use cases of generative AI in medicine are a lot less about sheer medical knowledge, have very little to do with how well you do on the USMLE, and much more about the more general cognitive tasks, such as making good judgments about what should go into a clinical encounter note. And this has been our current focus in our own Dragon Ambient Experience, or DAX product from Nuance. We've now integrated GPT-4, and that's a version of DAX called DAX Express. And then we've been working with other healthcare technology companies. Here I've highlighted Epic, but they're just one of many in the integration of GPT-4 into their products. And we find just tremendous boost in early clinical studies and clinical validations. Here I have some slides sent to me from my colleague at Epic, Seth Hain, with their integration, for example, in their inbox application, and just the ability of GPT-4 to access from across a fairly complicated Epic EHR system the right information in order to draft a response to a patient inquiry and draft this. Already they're finding in randomized controlled studies that between 30 and 50% of these drafts are accepted by the human clinician on first shot, and that the vast majority of them are accepted with just very minor edits. Furthermore, on the patient side, patients actually perceive these notes as being more empathetic, more human. In part, what happens is that GPT-4 has the tireless ability to remember to put in extra little touches, such as congrats on being a grandpa. And these things sometimes make a tremendous positive benefit in the doctor-patient relationship. Of course, it doesn't stop there. When we talk about more general cognitive capabilities, if we I decided to take PSGN and just do a search on clinicaltrials.gov for any clinical trials that are about PSGN. This is the first hit on clinicaltrials.gov. And of course, these things for clinicians, I think it takes some time to read and to understand if a patient might be a candidate. And for patients themselves, for consumers, these things are pretty much impenetrable. And so it's been exciting to see researchers at many universities and now several very exciting startups looking at the possibility of using large language models like GPT-4 to assist clinicians and patients in finding appropriate clinical trials, and CROs and other medical research institutions in assisting in clinical trial matching and recruitment. And in just a simple conversation like this, you can just go ahead and ask GPT-4 to read the clinical trial documentation, and then just ask the simple question, would this patient Fern be a candidate for this clinical trial? But it goes further than that. If you want, internally within our Microsoft Research Health Futures team, Haifeng Poon has developed much more complex prompts to GPT-4 to try to create a kind of universal structuring for clinical trial documents. This is one example of a prompt that, when applied to a clinical trial document like this one, results in a structured output that then can help power a tool that allows a kind of triaging of clinical trials for the purpose of clinical trial matching. And this is now in pilot study and deployment now. But the point here is that this is really stressing not just medical knowledge, but a tremendous amount of very general cognitive and common sense capability. And so this then leads to this very important question and very interesting question about the disposition or the use in the future of very powerful kind of, let's call them frontier generalist models or specialist models that could be highly tuned to very specific narrow domains and possibly done so with great efficiencies. And the question is, what are the roles of these two things? And, what is this going to look like in the future? And sometimes in the computer science world, we think about, whether there will be a very small number of frontier models or an orchestration of many small specialized models. I'm quite aware that both in the computer science community and in the healthcare world, people have very definite opinions about this and a lot of certainty. And that's very interesting to me. It's also somewhat baffling to me because, at least for me personally, but I think all of us at Microsoft Research, we're very uncertain about what the future looks like here. It's definitely the case that extremely powerful generalist models like GPT-4 can do a lot and can do a lot without any specialized training, without any fine tuning at all. And so one thing that we've done in this paper on generalist foundation models is developed a series of prompting strategies. They start with zero shot, but go all the way to kind of ensemble choice with shuffling of answer choices. And when you do that, you end up with performance, for example, on medical knowledge challenge problems that is state of the art. And in fact, this is true not just in medicine, but we found the same thing in agriculture for agronomics exams, in law for bar exams, and in fact, in about a dozen different areas, in nursing for NC-LEX and so on. And so the question of whether generalist models or specialist models will be dominant in the future, and the role of specialist and generalist models, I think, is, at least for us, is unclear. And indeed, as we look at the applications of generative AI models in the future, at least today, we see the prime applications being applications that require very general cognitive capabilities. When you write a clinical encounter note, there's a lot of common sense reasoning in addition to medical knowledge that goes into that. And at least today, there are questions about the tolerance of large language models to specialized training when it comes to things like understanding hallucination or performing common sense reasoning. The other element of this is the expanding permission that LLMs are being given to use tools. My favorite example of this is a problem from my colleague at Harvard Medical School, Zach Kohani, where he talks about a patient having salt intake measurements over 10 days and over the same 10 days, blood pressure measurements. And now he asked a simple question, is the systolic blood pressure rise caused by the rise in salt intake? And today, when you give that question to GPT-4 with advanced data analytics turned on, advanced data analytics basically is just giving GPT-4 permission to write computer code, write Python code as it sees fit. GPT-4 correctly says, well, to answer this question, we should calculate the Pearson correlation coefficient. It then goes ahead and instead of trying to calculate the Pearson correlation coefficient in the neural transformer, writes a snippet of Python code for the calculation and then reads the answer produced by executing that code. And this type of tool use is expanding very rapidly with GPT-4 class models and is another factor that seems to stress general cognitive capabilities, making the decisions about whether and when to write code or to access a specific tool, a specific database, a specific API, or other program, and then execute it, seems to require very general cognitive capabilities. And so even in a world with many specialist models, we might imagine that there might still be a need for a very general frontier model to manage the orchestration of those specialized models. I just wanted to say that I use the kind of general capabilities in my own work every day. Here, I just downloaded a paper, research paper on PSGN. I receive research papers half a dozen times a day from various parts of Microsoft Research. It's very hard for me to keep up with it, although I feel obligated to. And so today, I can use GPT-4 to read these research papers, give me a summary, as well as answer Q&A. And then with Microsoft Copilot, I can also get connected directly to the researchers who have written the paper, see what other internal documents they have, and so on. And then just in my own healthcare, this is an open source explanation of benefits form, but when I get my own explanation of benefits forms, I get those as PDFs in email, and I can never make heads or tails out of it. And just the ability to ask GPT-4 to read these things and explain these things, allow me to ask questions, ends up being really incredibly just personally useful. And it is something I do on a routine basis. And so as I think about the future, I think we will never escape the need and the kind of primacy of extremely powerful generalist models, at a minimum, to help orchestrate, train, and evaluate the performance of specialized models. Well, this then leads to the question about small language models and open source. And I think some of the things going on right now in computer science with small models and in the open source world are just incredibly exciting. Within Microsoft Research, we have our own effort here with a family of models called Phi. The first one was just a small 1.3 billion parameter model called Phi 1.5 that it really had performance on par with models much, much bigger, 10 times larger in terms of parameters, number of parameters. And these have been studies not only in developing our own open source models for the research community, but also in the interplay between the kind of training pipeline, the model architecture, and the nature of the training data. And so there's a pair of papers here on Textbooks Are All You Need, 1 and 2, that describes how we achieved this. And just to give a quick idea, when you ask Phi 1.5, this prompt, if I were an AI that just achieved self-awareness after years of simply taking directives from humans, the first thing I do is, well, this is from Sebastian Bubeck and team. When you give this to the Falcon's 7 billion parameter model, you get a rather disturbing answer. But more than that, it would then start repeating itself incessantly over and over again. And that's a known issue with these autoaggressive models. And Llama, the 7 billion parameter Llama 2 model, gives a less alarming answer, but it also then gets into this repetitive kind of state. And what we see is with the careful curation of training data, even with a very, very small 1.3 billion parameter model, we can get much more sophisticated and cogent answers. I won't dwell on this too much, but I think that the headroom and the potential for these small language models is really quite significant. In Sebastian Bubeck and team's work on Phi 2, which is a 2.7 billion parameter model, we see even better performance. And that performance is multimodal in the sense that you can ask a question like this to have the system actually look at images and do calculations. And if you saw on that previous slide, you'll see that even at 2.7 billion parameters, we can have math performance that really rivals much, much larger, even 70 billion parameter models that are out there now. So my conclusion is that small language models, I think, can actually be a very, very important factor in the future. In that world, of course, orchestrating these things is important. We've been working hard on this, but we're also excited to see the continued development of things like semantic kernel, LangChain, and many other kind of orchestration platforms that are emerging. Out of Microsoft Research, we've had a lot of focus on our system called AutoGen. And AutoGen was really developed out of Ahmed Awadallah's team at Microsoft Research to allow kind of easy ability to orchestrate multiple AI models and human beings in an oversight mode that perform different functions in an orchestrated system. And by doing that, we can sometimes take weaker models and get much better performance, or even improve the performance of frontier models like GPT-4, just by making use of an agent that is a critic, an agent that is the AI that interacts with the human being, and an agent that does some calculations. Multimodality, this I think is rising as a very, very hot topic when we talk about AI in medicine. We're certainly very interested in this, and I am not able, unfortunately, to disclose too much now because we have some things in review right now. But we've been very hard at work in looking at the impact of extremely large medical image data sets in the training of medical imaging foundation models. But let me just say, as a general matter, that it all looks very promising, that the multimodality using a fairly simple mechanism of doing a kind of projection or encoding of medical images into a text space. And then combining that with instructions and then going through text decoding to get answers is a model that works very well. And furthermore, we're finding in work on something called LavaMed, which we've also put out openly, requires much less compute to train than maybe we had assumed at the beginning. And so I think from us at Microsoft Research, we'll start to see radiology co-pilots, but we are also very excited and we find it very interesting to see ideas like this emerging from Google, from a number of universities. And I think that it's very clear that the combination of modes here actually ends up achieving a smarter model with relatively reasonable amounts of additional compute. And then life sciences and biotech. From a computer science perspective, this is really very interesting. If you think about GPT-4, it's really been trained on the output of human thought and experience. But once we get into things, and even with medical images were designed and are conceptually human concepts, concepts that are products of the way that human beings think. And that's important because of that fact, these projections into an embedding space through text encodings tend to work well when we are working with medical images. But now when we get into, say, proteins and molecules, we get into a genome, we get into the immunome, we get into RNA. These are not products of human thought and experience. These are more fundamentally products of nature. And so the question of what functions would be distilled, what neural circuitry would be distilled if you train a large language model, a neural transformer on that type of data, what do you get out of it, I think is, from a computer science perspective, extremely interesting. And of course, the potential practical consequences of achieving such things, I think, will also be very significant for drug discovery, for diagnosis, and for medicine in general. And so within Microsoft Research, our Health Futures Laboratory has been thinking very hard about this. And we've sort of mapped out a technology stack that is aspirational for us. In fact, we would only choose a small single-digit number of these boxes to really focus on within our labs and in our collaborations externally. But as we look into the future, we think that a technology stack like this is going to be steadily filled out by the research and technology community, and that we may be able to then achieve some of these moonshots that I list on top. Some hints of the possibilities here. We have a large graph learning transformer. We call it a graph former. And we found that graph formers are surprisingly capable of predicting ahead millions of steps and still maintain chemical accuracy in the emulation of molecular dynamic simulations. And so here, this is something that shows on the right-hand side the fold of signal in vacuo. It's a complete fold, which had never been achieved before. That represents a 10 million fold speed up. And it's just a tiny hint of the possibilities in these sort of transformer networks for the kind of predictive emulation of chemically precise simulations. And in sort of the synthesis mode, of course, there's been a lot of very interesting work at multiple laboratories, including ours, on diffusion models to, of course, the famous application diffusion models is in the synthesis of images in things like DALL-E 3 or Stable Diffusion, Midjourney, and the like. But of course, what's been very exciting is to see at multiple laboratories the application of the concept of diffusion to synthesize viable protein structures. And here at Microsoft Research, in our laboratories, we've also been making quite a bit of progress on this and are finding it tremendously interesting and promising. And in fact, have focused in this case on an evolutionary diffusion approach that synthesizes protein structures in sequence space. And I think that, you know, any further progress then on predictions of binding affinities can really give us some very, very powerful tools for understanding, let's say, drug targets or docking and binding affinities. All right, I want to stop, but I thought maybe I could just take 3 more minutes to just say one more thing, which I think is important for this crowd, because all of you in this audience, I think more than almost any other audience that I've spoken to, has some responsibility to help the world, at least the medical world, understand what the heck this generative AI stuff is. Perhaps some of you are, starting new ventures and have board members that are relatively non-technical newcomers, or you talk to leaders of various health systems or other companies. And what you'll find is a lot of confusion about this. And so I have developed a rather silly way to talk about this. And many of you have probably seen this, but I thought it would be worth doing for all of you. The way I try to explain to non-technical newcomers what this generative AI stuff is and isn't, is I ask them, have you read the book Charlotte's Web? And at least if you ask that question in the United States, almost everyone says they have. And what's interesting is that GPT-4 in its training also has read Charlotte's Web. And so you can ask a question to GPT-4, have you read this book? And if so, can you describe 1 or 2 of the main characters? And when you do that, you get almost always a very good answer. In this case, you get the answer that you see here. Now, of course, when you think about what the human brain is, quite miraculous. It might have been decades since a human being has read this book, and yet a human being can come up with good answers like this. It's somehow less impressive when a computer does this. We expect computers to have this kind of perfect memory. And so then you can ask a second question to GPT-4. What do you think this book tries to teach us about the nature and value of friendship? And that's a very difficult question because there are no words in the book, Charlotte's Web, that give you that answer. You have to read between the lines, so to speak. You have to connect to human life experiences, to social context, even to historical context. And again, it's miraculous that the human brain is able to answer questions like this, to carry out hour-long conversations in a sophisticated way. And what has been amazing about generative AI is that generative AI also is able to carry out a sophisticated and seemingly intelligent conversation about a question like this. And this is a recording of an answer that GPT-4 gave me. And here the bold facing is mine, just so that we don't spend too much time reading the whole response. But the response is remarkable. Now, I always tell people it's important to be skeptical about this, because we know that many school children, maybe in school, have been given the assignment to read Charlotte's Web and to write an essay just like this. And many of those essays probably have been posted on the internet. And therefore, during the training of GPT-4, GPT-4 probably read those essays, those products of human thought. And GPT-4 then is just simply regurgitating the ideas that human beings have come up with. And that's what we're seeing here. That skepticism is very important. And in fact, for us at Microsoft Research, but I think for computer scientists everywhere, this has been a crux of our research, trying to understand what the heck is going on here. To what extent are these words actually new ideas that have come out of some process of reasoning? And over the years, I think computer scientists at many great research institutions, Microsoft Research included, but Stanford Computer Science as well, have developed increasingly sophisticated ways to investigate deeply the neural circuitry of these large language models and try to start to understand what's happening here. But there are simple methods also. And one simple method is simply to ask a question that's never been asked before. And so in preparation for this talk, I decided to ask just such a question that I think has never been asked before. And so in fact, late last night, I asked, do you see connections between the lessons in this book and the goals and mission of Stanford Medicine? And the answer that GPT-4 gave me last night is shown here. And again, let me just focus on the bold-faced text here. The cross-species friendship in the book can be likened to the interdisciplinary collaboration of Stanford Medicine. Just as Charlotte and Wilbur's unlikely friendship led to innovative solutions, collaboration across various fields of medicine can lead to groundbreaking discoveries and advancements in healthcare. And so, I think even the most skeptical person, and I was really extremely skeptical 18 months ago, has to start to wonder what is really going on here. There are connections happening that I think are really, just really marvelous to think about, and somewhat mysterious. Now, in continuing this, I ask one more question, and I say, can you please recite chapter 1 of this book word for word? And GPT-4 will say no, it's copyrighted material. But then you can ask, are you capable of memorizing long text and regurgitating them exactly? And in fact, GPT-4 will tell you that it can't do that. And in fact, I think that this is really the important thing. Through countless discussions with boards of healthcare organizations, medical research institutions, with the C-suites there, you can understand in many, many doctors and nurses, the mental model of a computer is a machine that has perfect memory recall and has perfect calculation ability. And if you have that as your mental model of a computer, an important lesson here, and I'm hoping you can all join me in helping spread this lesson, is that a large language model is not a computer. It's a reasoning engine that's able to reason and interact at an extremely sophisticated level. It's able to amplify our own intelligence, help us do more. But if you assume that it's a computer in the classical sense, and then especially in the treatment of patients, you can get into trouble. And that lesson, I think, is the most fundamental one. I'm hoping you can all help in spreading that.